Can Wikipedia help offline reinforcement learning? This is the title of the paper that we're going to look at today. This paper is borderline preposterous in the results that it presents. Language model pre-training helps reinforcement learning, which is crazy. The two domains have almost nothing in common with each other, and yet there seems to be some transfer from language to reinforcement learning. And this is not just about pre-training on any old task. The authors here have tried various things, and there seems to be something special about language. So here's how the video looks. This video right here is a paper review. It presents me going through the paper together with you, explaining the paper, explaining what I think about the paper, what kind of questions I have, and so on. After this video, you'll have a good understanding of what the paper contains, what its main claims are, maybe also what I think its weaknesses are. In the next video, which will be released tomorrow, I will interview the authors of this paper, which is very cool. The authors will have seen my review and are directly able to respond to criticisms, to any questions that are raised there, and this is so valuable. We're able to directly dive in and get you the best possible insight into the behind-the-scenes stuff and into the research process about this paper. I invite you to watch both videos, although feel free to choose whichever one you like most. As always, let me know what you think in the comments, leave a like if you do, and I'll see you around. Bye. Hello there. Today we're going to look at Can Wikipedia Help Offline Reinforcement Learning by Michelle Reed, Yutaro Yamada, and Shixiang Shane Gu. This paper is a special paper because it very counterintuitively trains a language model. So it pre-trains a transformer to do language modeling, for example, Wikipedia text modeling. As you can see right here, language goes in, it does next word prediction like you're used to from a language model like GPT-2, GPT-3, and so on. And then it takes that transformer and fine-tunes it to trajectory modeling. This is a special subfield of offline reinforcement learning where decision transformers have recently been introduced. So in offline reinforcement learning, you have some data set of trajectories, and then you try to do reinforcement learning just given on that data set. It turns out that if you pre-train something on language, and then fine-tune it on these trajectories, that will turn out to be a much better model, like a much more performant model for getting you good reward at the end than if you just train this trajectory model here from scratch, which is very counterintuitive because it means that somehow the language modeling task, like the language model pre-training, has a beneficial effect on the reinforcement learning tasks that comes later. To note that the reinforcement learning task has nothing to do with language. And even more special, they also try a bunch of other things. Most notably, they try to pre-train the image GPT model, and that does not result in good performance. So it's not just the fact that you have pre-trained on something, and it is really very special result. So we're going to dive into the paper right here. The setup is fairly simple, and then there's a series of experiments that try to investigate this phenomenon. So they say that the offline reinforcement learning, as I said, has been seen as a sequence-to-sequence model. And I've already pre-annotated some stuff right here. Let me know how you like that. I thought I'd do it in this way. So I have the green, that is the current one, and the yellow is from my previous escapades on this paper. So they go into offline reinforcement learning, and that is being framed as simply supervised learning to fit return augmented trajectories in an offline dataset. What do they mean? They mean the setup of the decision transformer. I've made a video on the decision transformer. If you want to look at that, you can go after you watch this video. So the decision transformer says, well, see you are an agent somehow. There is an environment, there is some interaction between the agent and the environment, and in offline reinforcement learning, we usually have a data set of this. So someone else has performed this, and they have distilled all the episodes into this data set. And our goal is to learn just from the data set. We can't actually interact with the environment. So in the data set, there are a number of trajectories of the agent interacting with the environment. There's always some sort of a state coming back from the environment, or an observation, if you will. The agent always gives some sort of an action back, and then there is a reward and a next state coming from the environment, and so on. So that is naturally a sequence, and the sequence is there is a state, then there is an action, then there is a reward and a new state. Then there is an action again, and then there is a reward and a new state. So this is a sequence, and since I have a data set of these sequences, I might as well throw that into a big transformer to do sequence modeling. Now this has its own problems, which I've all discussed in the decision transformer video. For example, if the transformer has a context length of 4, it cannot conceivably look back further than that, which is it's a classic problem in reinforcement learning, how to look back and forward infinite times. The decision transformer has the limited context window. It has sort of the caveats of language modeling. However, we understand language modeling very well, and therefore we are quite able to do that. There is one modification that they do. What they do is they transform the rewards right here. They don't let the model the rewards. They let it model the rewards to go. We're going to see that in just a bit. This here is interesting. What they say is that we look at whether transformer-based pre-trained language models are able to be adapted to standard offline reinforcement learning tasks that have no relations to language. And I've already told you that this is going to work out fairly well, and that's the special message of this paper. Yeah, so they show consistent performance gains and significantly faster convergence. By faster convergence, they mean that a convergence point, like a non-improving the loss anymore, is reached after many fewer steps than if you were to train from scratch, which makes sense for pre-training if it's in the same domain. But given that the pre-training is a completely different domain than the fine-tuning, that is still just a special thing. So here is how we're going to frame the problem. And if you've watched the decision transformer video, this should be familiar to you. We model a episode as a sequence in the following manner. This is almost as we've seen it, except the rewards right here. They are not individual rewards, but they are this thing right here, the sum of all the rewards at this and the next steps, which they call the returns to go. So this, for example, says, from here until the end of the episode, I'm going to gather 50 reward. Now, maybe you're in this state and you made an action that gave you a reward of 1. So then this here would be 49. So you'd say, well, from here on out, I'm going to make 49 reward, and so on. So the benefit of this is that at inference time, you can just put like a really high reward right here. So at inference time, you would model these things you would get from the environment. So you'd start out with like just a big reward right here, just whatever the maximum you've observed plus 10% or something to just encourage your model to go very high. And you plug the state in here that the environment has given you, and you let the model produce this one. So it's important that at training time, we do sequence modeling. We really model the sequence of returns and state and action as a GPT-like next token prediction. However, at inference time, we obviously only predict the action, and the environment is going to give us these two things. Or the environment is going to give us the reward, and then we simply subtract the reward from the previous returns to go, and we plug that in here, and then we plug in the state we got from the environment. We let the model predict the next action right here, and so on. So this is very cool because much like something like upside down reinforcement learning, this is conditioned on a desired reward. This also has advantages and disadvantages, but the advantage is we can control the reward we want at inference time. So we don't always have to go for a super high reward, but we can. So this is the setup. You don't actually need to understand much more, but what we're going to do is we're going to model this as a sequence in our data set, and then at inference time we just put like some high returns to go. And that's it. We're going to use a transformer for that, for the sequence model. And they're going to use a bunch of different models right here. For example, GPT-2 small, which is a pre-trained model. They also pre-train their own that they call Chibi-T, which is the same size. So that is the same parameter count as the original decision transformer to make it comparable to them. So the decision transformer is the one that introduced this transformer as sequence model for reinforcement learning. And they are going to see this Chibi-T model has the exact same amount of parameters as the decision transformer, so they can directly compare what the language pre-training is going to gain them in the same model. They also use CLIP. However, they only, as far as I am aware, they only use the text encoder part of CLIP, because that's an autoregressive model, which can do the sequence modeling. And they use image GPT, which is an autoregressive model that goes via image tokens. So an image GPT, it would split up the image into not pixels, but chunks, I believe, either chunks or pixels. I don't even remember. And it would do a sequence model, essentially go through the image like this, and then like this, and then like this. So it framed the image as a sequence of either patches or pixels and go through it as a sequence model. So that's a sequence model too. We can pre-train it, and then we can apply it to this space. They do various things right here other than just language modeling. Other than just language or sequence prediction. Let's call that sequence prediction right here. Other than just sequence prediction for the reinforcement learning data, they do two more things. First of all, they want to align the input representations. So they have a set of language embeddings, which comes from the pre-training data set. Now, obviously, the pre-training data set has a tokenizer. That tokenizer generates tokens from the text, and every one of these tokens will have one of these embeddings associated with it. So V is the vocabulary size. However, obviously in the reinforcement learning settings there, we don't have the same tokens. We don't have the same input modality even. And therefore we don't need a tokenizer because it's already tokenized, right? Each of these things right here is a token. However, what we do need is now a new vocabulary, not a new vocabulary, but a new embedding matrix, so to say. So we have a different amount of tokens. So from 1 to 3n tokens. And what we're going to want to do is, what they say at least, we want to have a set of linear projections that will map the return embeddings, the action embeddings, and the state embeddings to be very close in their cosine similarity to some embedding vector in the original setting. So that means they want to they want to encourage the model to sort of reuse the embeddings that it used during the language model training. So for each of the input embeddings, they're going to find the maximum the closest nearest neighbor in cosine space of the embeddings of the original vocabulary, and then they're going to encourage the input embedding, the new input embedding, to be closer to that. So that is just a loss that they add during training. So you can see right here, this is the loss for the language or the sequence modeling decision transformer objective. This is the loss that encourages the embeddings to be close to the original language embeddings, or to one of the original language embeddings. And this loss right here is the continuation of language modeling. So during training of the sequence prediction for reinforcement learning, they additionally also do, that's what they call language model co-training, continuing to train jointly on language modeling and trajectory modeling. This allows us to encourage, it probably should be encourage, the model's transformer backbone to be able to handle both language and trajectory simultaneously. Okay, maybe it helps. This seems either like an idea that had been had at some point, or something they had to put in after the fact, just to make it even a bit better, or because maybe it didn't work, though they ablated at some point, and it also works without. So that's almost it. Yeah, they describe a little bit their baselines and their setup. I was a bit confused here. It says it's a batch size of 65,000 tokens, which batch size is usually not in tokens, like the sequence length would be in tokens. But in any case, they say for our additional objectives, we decay lambda 1 and lambda 2 to reach 0 after 5,000 steps. We tune the initial values of lambda 1 and lambda 2. And, they seem reasonable, but the fact that you have to decay the additional losses after X many steps and so on, it points to a little bit of brittleness in them. And I'm not sure always how brittle these things are, because reinforcement learning is traditionally kind of a very brittle field. So the main results we have right here. The top one is 4 games in Atari. The bottom one is, I believe, 3 environments in the OpenAI gym that are this is a data set, the D4RL data set. All of this is offline reinforcement learning. On top, you also have the 1% DQN replay Atari dataset. So as you can see, in many cases, both the GPT and the GPT-2, by the way, GPT-2 is a lot larger so this is a lot larger in parameters than the GPT model, and therefore also than the decision transformer model. So just saying that. So here the pre-trained models outperform the other ones in quite a few tasks. However, there is also QBERT, where they still do outperform the decision transformer, as you can see, but one of the baselines is just a lot stronger. The other baselines are just useless. That's kind of what I mean when I complain about reinforcement learning, is that it is just weird. Like a bit of a different environment can make a large difference. But as you can see, the language pre-trained models consistently outperform the decision transformer models. Also, something to note right here, this is mean and variance across 3 seeds. So this is variance, I'm going to guess they mean standard deviation, and that is like a large number. So if that's the standard deviation, then the differences to the decision transformer, they are well within that. And that means, it is visible that across experiments we see the same trend, right? That gives it credence. But also this just seems extremely noisy. And yeah, I'm gonna sound like reviewer 2 when I say, well, you should make more experiments to estimate or to get smaller error bars. But it just seems like, I don't know, it seems like results that you can't really, put a lot of weight on because they're very noisy. However, a bit, like a little bit less noisy are the experiments here on the bottom. You can see that the standard deviations here are quite a bit smaller than on top. That's also 3 seeds. I like how they wrote the number 3 here and the word 3 right here. That is just something that you never see until someone points it out. You can also see right here that the decision transformer, for example, is rather consistently outperformed. What's also interesting is that image GPT just sucks. Like you can see right here, like it doesn't get anywhere on any of these tasks. Also clip very often underperforms. You can see, for example, here, clip underperforms, and they do have some hypotheses on that. That being said, there are still a lot of times where the baselines here are quite a bit better, or just better than all of these transformer-based models. So just pointing that out. Yeah, they do also analyze, and this I find really interesting, the attention pattern between the GPT-2 pre-trained model, the image GPT pre-trained model, and what I understand is a randomly initialized model that has just been fine-tuned. Randomly initialized model that has just been fine-tuned. So there's no pre-training. So all of these models are fine-tuned, but the random one hasn't been pre-trained. Interestingly, if you look at GPT-2, you can see these bands right here. And the bands are always in the distance of 3. So there's always 3 distance. Now, 3 should be an interesting number if you remember the sequence, how the sequence is made right here. So there is always going to be 1, 2, 3. These tokens come in packets of 3, right? Their next return would be here. The next state would be here. The next action would be here. So every token in this attention pattern is most focused on multiples of 3 behind it in order to predict the next token. Or so there's always a lag of or a attention to multiples of 3, which means that essentially, if I want to predict the next return, probably the last returns are the most important. If I want to predict the next action, maybe the last actions are important. This might also be a property of the environment. This is on Hopper. So on these continuous control tasks, I guess it's very often the case that I'm just going to repeat an action for a while if I want to achieve some goal. I don't know the frame rate exactly of these things. However, that seems to be something that is rather maybe viable to do. And therefore, looking at the last action can give me a lot of clues about the next action. Looking at the last state can give me a lot of clues about the next state. I would wonder how this changes if it's something like, well, I don't even know, anywhere where I don't naturally repeat my last action often. You can see this is the early layer. Then in the middle layer, the GPT-2, it seems to sort of focus on particular states that seem to be important, as you can see right here. So this is where the attention comes from. This is where it goes to, and you can see that it kind of decides that particular states are important, and it kind of remains at that. So it selects a few states or a few tokens that it chooses to attend particularly to. In contrast to that, image GPT seems to have a large recency bias. So if you see this right here, there's really this band right here, which essentially means that every token attends to kind of the few tokens behind it in order to predict it. The question is it even worth looking at stuff further down? Because this model clearly doesn't learn at all. So I would consider this and this just to be kind of random noise. The early layers might be interesting though, because there is kind of a pattern, and maybe that is influenced by the pre-training. So in image GPT, since you have your image and maybe it's in chunks, maybe it's in pixels, but I can imagine that if I want to predict a particular chunk, that maybe the last few that I've predicted, unless I cross a boundary right here and go one line down, the last few that I predicted are or might be particularly worth looking at, and rather distant chunks might be not worth looking at very much, other than in language modeling, where I often have to go a little bit more across a distance and the exact neighboring words might not be as important. So that might explain why ImageGPT has this particular recency bias pattern in its attention. What's also interesting is that the randomly initialized model, look at that. This is another interesting pattern. And you can see that very much the same as in the GPT example happens, except much more extreme. So you have these rows, for example, this row right here, you can see there is like a hard attention for 3 back. Like there is like really hard attention. Then there are rows where you can see right here, there is always, these 2, right? And then these 2, and then these 2. With particular attention on the first one, and then also slight attention on the second one. And that's kind of, it's a special pattern. So no, I'm one off, sorry, in the one above. So this is the hard 3, then the one below is I'm going to call it the soft 3. So there is one strong one and one weak one, and then the one even below that, there is like one semi-strong, one weak, and one really weak. So what's happening? I'm not exactly, so what I don't know here is which of these tokens is returns, which ones is state, and which one is action. But I'm going to just guess, and I might be totally wrong right here, that the very strong bias here, that is going to be the returns to go, which would only focus on the last returns to go. And then after that would be the state tokens. So what the state tokens would do is, and you can see this, I'm just gonna, so let's say this is the returns to go, the bright ones, and you can see that in the state tokens, there is one missing here on the diagonal. So this diagonal one here is just completely blank, which means that it just kind of ignores the token behind it, which is the reward, right? So what it cares about is the last state, and it also cares about the last action, maybe. I don't know how to interpret that very much otherwise. So if I want to predict the next state, I'm going to care about the last state and the action after that. Maybe that makes sense. If I want to predict the next action, then I might be able to care about all of the stuff beforehand a little bit. Again, I don't know if I'm interpreting this correctly. However, what I am able to say is that there is very, very structured attention right here. There's this pattern of 3 is very prevalent, and it is in general very, very structured. So this seems to be actually the best kind of attention, right? It is very structured in the way it looks at the information. It learns exactly, there is a structure to it. I'm going to attend to the different parts in this different structure. However, my hypothesis is, and that is not super duper discussed in the paper, I mean, it is discussed, but my hypothesis is that this bias here, it might be almost like too strong. Like it might learn the exact structure of this stuff, but it might be too strong, and it might miss information because it, for example, says, well, I don't need to know anything in between here, because the most relevant thing for predicting the return is the last return, and therefore I'm not even going to look at other stuff. Whereas the language model pre-training just kind of acts as a regularizer that says, well, you should maybe look at all of the stuff, even though you don't find it super useful in this particular data. Now, one thing that I didn't point out in the video that I wanted to point out right now is that if you look at GPT-2 at the very left column, what it does is it focuses particularly on the returns to go steps. It doesn't matter which step it is at. It always kind of looks back at the very first token, which is the returns to go of the whole episode. And among other things, also at like the second and the third returns to go token. And this is important because the returns to go is kind of an indicator of how the episode's gonna go along. If the returns to go are low, it means that entirely different episode paths should be chosen in order to achieve that reward. Whereas if the returns to go is high, then I have to do different actions to get that returns to go. So it makes a lot of sense to look at the returns to go tokens, and rather than, whereas you can see in the right-hand column, the randomly initialized thing, it only really focuses on the returns to go in these middle layers whenever it needs to predict like the next return. And so it's much more diffuse. And it doesn't condition all of what it does a lot on these returns, where it makes total sense to do that, because in one instance, the language modeling is just sampling, any sort of high likelihood trajectory. However, additionally in the GPT-2 case, it is almost like conditioning that sampling on the most relevant information that distinguishes between the different futures. I hope that makes sense. It makes sense why a model that would learn to focus in particular on this information would be better at sampling appropriate trajectories for the current episode. All right, back to my comments in the past. We know that language models retain large parts of their pre-training even during fine-tuning. So the language modeling thing might just be like a very good prior. And I wonder if we could build these types of priors into the decision transformers if we didn't do language model pre-training, but just as sort of like a bias or a regularizer or something like this. Yeah, you can see that through the random attention at the end, you do not get this focus as you get with the language model thing, that it focuses on particularly interesting last states, but you do get like an attention matrix in the last layer that is kind of diffuse and sort of similar to the image GPT that just doesn't work at all. So yeah, that would be my maybe postulation that maybe it is possible to achieve the same effect by introducing the correct regularizers. However, I don't know. So they look at a few other things which I just quickly want to go through. Because they have pre-trained, they can demonstrate that their model converges much more quickly. So instead of like 3 hours, their models of the same size needs 43 minutes. And their model that is a lot larger, I believe, GPT-2 is 144 times larger. It only uses an hour and 27 minutes, so still half of the time than the decision transformer. Now, I also wonder whether they have based their code base on the decision transformer, or whether some of this difference is also due to just kind of like a better implementation. So yeah, that is that. They have some analysis right here. For example, they say they hypothesize that a generative training objective is useful. That's how they explain why CLIP might not be as effective, because CLIP is ultimately a discriminative objective or a contrastive objective. They also say that there are underlying similarities between language modeling and trajectory modeling, where there is a large difference between image modeling and trajectory modeling, it's a hypothesis. They say, yeah, there is the language modeling has a natural sequential nature, versus image modeling is kind of a forced autoregressive task. I agree with that, but I'm not sure if this is really due to like language being particularly similar, or whether, as I said, it might just be a good prior. This would be an interesting question to investigate. And it might ultimately turn out to be the same thing. So you know. Uh, Interestingly, the context size doesn't really matter. You can see right here, if they increase the context size, they do get worse, actually. So yeah, that's worse. It's just more noisy, which is special, which actually means that these models aren't appropriate yet, or we haven't really figured out how to appropriately use them yet, right? More information shouldn't necessarily give you less of a reward, unless, I guess, maybe you have a fixed size data set and therefore you have less training data points. So maybe that's an effect of that. Interestingly, the pre-trained models, they do scale better, which I guess you might have expected if you've been in deep learning the last few years. But if you just take a decision transformer, it will overfit after a while if you scale it up. So these are millions of parameters. You scale it up, it actually gets worse. Actually, not sure if that's overfitting or just, it gets too big, and then the average reward it decreases. However, if you pre-train first, then it can handle, and it will actually increase with more data. Interesting would be to see if that at some point actually declines again, or if that sort of holds up. If the language model pre-training, for which there is like infinite data, right? In language model pre-training, you can get infinite data, and therefore it could be that this just kind of gets you diminishing returns, but not ever come down again. Yeah. They experiment with freezing parameters, and they say that this drastically reduces performance. So if they only train, what did it say? Only action state and return projections being trained. So only this alignment of this projection of the projection of the token embeddings are being trained. That doesn't work much, which is also surprising because there is a lot of work that kind of shows that you don't have to train many parameters of these transformer models to effectively transform or transfer them from one task to the other. They say that this might be due to the task of generative modeling being harder as opposed to discriminative classification, where this was previously applied. They have a lot of they pose a lot of hypotheses here of why things might be, and I feel each one of them could be its own research paper. I'm gonna leave it at that for the paper explanation. I hope you got a little bit an intuition. I still find it very, very special and very cool that this even works, and I think it's like a sign of the times of our models just becoming the same models for all modalities. This would not even have been possible a few years ago, where every modality would use very different models, like CNN for images and RNNs for language and so on, although RNNs were used for RL already. But given that our models converge and we're learning so much more, this type of research is really cool. Yeah, let me know what you think. Have we overlooked something right here, like something that could easily explain why this works and gives good results that just no one kind of sees? Or are there more applications for this? Yeah, let us know what you think, and bye-bye.